Cans of regular Coke are labeled to indicate that they contain 12 ounces. In the reading notes, you are given a data set containing the volume in ounces of 36 different cans of Coke from a random sample. You should have found that the sample mean, X bar, is 12.19 ounces, and the standard deviation of the sample was 0.11 ounce. According to the information printed on each can of Coke, Coke cans are filled so that the mean is 12 ounces. We will use a standard deviation of 0.11 ounce based on these sample results. Use the properties of the central limit theorem to find the probability that a sample of 36 Coke cans will have a mean of 12.19 ounces or greater. What do the results suggest? So first, let's just make sure we understand what we're looking for here. According to the manufacturers of Coke, the mean volume of a set of Coke cans, of a sample of Coke cans, should be 12 ounces. But we found a set of 36 Coke cans, and the mean was 12.19 ounces. So we want to know what is the likelihood that a sample of 36 cans of Coke will have a mean of 12.19 ounces or greater. Is this something that's likely to occur, or is this a rarity that happened to occur in our set of 36 cans of Coke? Now, nowhere in the problem did it say anything about the volumes of the cans of Coke being normally distributed. But that's okay because our value of n is 36, which is greater than 30. So according to the central limit theorem, even if our original population is not normally distributed, if we have a big enough sample, in this case 36, we can use the normal distribution to make approximations and predictions about groups of individual data. So for instance, groups of cans, like 36 cans in this case. So we can use our normal distribution here regardless of what the original population looked like. Alright, so here's a few things that we know. If the original population had a mean of 12 ounces, that means that the mean of the sample means will also be 12 ounces. So right here, the mean of my sample means is 12. And I'm going to convert those to z-scores. So right there would be the 0 for the z-score. Alright, so I need to find the z-score, but I need to find it for the group of 36 cans of Coke, not just for one individual can of Coke. So I have to use the z-score formula that is a result of the central limit theorem. That tells us we take the sample mean that we're considering, in this case the 12.19, minus the population mean, and we divide that by the standard deviation divided by the square root of n. So the mean that we are considering is 12.19, and we're going to subtract 12, and we're going to divide that by the standard deviation over the square root of n. Okay, so let's simplify this a little bit. 0.19 in my numerator, and then I have 0.11 divided by 6 in my denominator, and this all comes out to be a z-score of 10.36. That's huge for a z-score, because remember we said that even positive 3 for a z-score is pretty darn unusual. So 10.36, that's really far to the right. So we'll put this z-score right here. So what that means is that a mean of 12.19 ounces would also be that far to the right. So there's a mean of 12.19 ounces. There we go. There's a mean of 12.19 ounces. Now remember, the distribution of the sample means has a much smaller standard deviation than the distribution of the original data. That's why, even though this is a difference, even though this is only a difference from 12 to 12.19, it's only a difference of 0.19, that's why it's so far spread out, because the standard deviation is so small. That's why 12.19 is so far away from 12. Alright, so now what we need to do is we need to find the probability, in this case, that a z-score is greater than 10.36. And by finding that, really what we're finding, let's paraphrase here, we're finding the probability that the mean of a sample of 36 cans is greater than or equal to 12.19 ounces. So by finding the probability that a z-score is greater than 10.36, or greater than or equal to, doesn't make a difference, we're finding the probability that if we took a sample of 36 cans, we're finding the probability that their mean is greater than 12.19 ounces. Well, if we go to our positive z-score chart, 10.36 isn't even on the chart. Anything 3.5 and up, we just say the area to the left of that is 0.99999. 0.9999. Anything 3.5 and up. So that means that all this stuff to the left is 0.9999. So this tiny little area here is 0.0001. So the probability that z is greater than or equal to 10.36 is 0.0001, or in terms of a percentage, 0.01%, very unusual. So let's talk about what this means. So we had this sample, 36 cans, the mean was 12.19 ounces, but the probability of that happening is so low, 0.01%. So we need to ask ourselves, did this really happen by chance, that we so happen to stumble upon a sample of 36 cans with a mean greater than 12, or mean of 12.19 ounces, when the probability of that really happening is 0.01%? Probably not. So this is where the rare event rule for inferential statistics comes in. We started by assuming that this was by chance. Well, when we realized how low the probability was of that actually happening, it probably wasn't by chance. There's probably something else influencing the results. So what this means is probably that the true mean, the true population mean, of the volumes of cans of Coke really isn't 12.00 ounces. So even though the can might say 12 ounces, probably what the Coke company does is they've probably found a way that they can still give a little bit more than 12 ounces to ensure that no cans of Coke actually go under 12 ounces. So even though it says it's 12 ounces, if you grab a can of Coke, you're not going to get anything less than 12 ounces. You might get a little more, but to make things more simple, the can just says that the mean is 12 ounces. So the true population mean of the volumes of cans of Coke probably really isn't 12 ounces. So what we would say, our sample was a typical sample and the reason why it was probably a typical sample is because the true mean is most likely greater than 12 ounces. So instead of us saying we got this rare event to happen by chance, 0.01%, probably didn't happen just by chance, meaning the true population of that really happening, or the true probability of that really happening is probably a lot more than 0.01%, but it's probably really based on a different mean. So if that mean was higher, the true mean was higher, and we found the probability of and we found the probability of a group of 36 cans with a mean of 12.19 ounces, it wouldn't be so far off, because this probably is really higher than 12.